Friends, in my previous session, I discussed clearly the necessity of the control signals while explaining what each control signal is all about. We have seen about 7 control signals plus 1 PCSRC, where it being a derived signal, and I told you what is assertion, what is deassertion, where all these control signals would be put in the data path model. All those things I clearly explained you. In this session, I'm going to tell you, or we are going to discuss clearly what would be the status of each of these control signals, whether it would be asserted or deasserted for this particular operation. This is what we are going to see now. First, let us take an R-type instruction where we need to now define clearly what would be the status of all these 7 control signals along with ALU op 1 and ALU op 2. So the 7 control signals, whatever we have discussed in the previous session, are REG-DST, ALU SRC, mem to reg, register write, memory read, memory write, and branching. Now for the R-type instructions, I am going to first trace what would be the status of all these control signals by looking into this diagram, because it is very easy for you to understand through this diagram. I mean, whatever data path I have drawn here, it would help you to understand it clearly. Before that, we need to understand what is R-type instruction all about. R-type instruction will have RS, RD, RT, all the 3 in picture. So the RS and RT will be added and the result will move on to RD. This is the regular tradition that we follow with R-type instruction. Now, how it will work, what are the signals that will be asserted, what are all the signals that will be deasserted. Asserted, deasserted, I have already told you what is the difference between these two. So please remember it. If not, please go back to the previous video, get it a clear understanding and then come back here. Otherwise, it is going to be difficult. Now see the status. I am going to use RS. So for sure, I will use RS here. I will use RT here. So RD comes here through this 1 and it is also in. So I need to also note RD. So REG-DST status will be 1. REG-DST is clearly high for R-type instruction. Now the first signal is cleared. REG-DST is high for R-type signal. Now the next signal that we need to worry about is very simple, ALU SRC. What do you mean by ALU SRC? That's the signal that's going to be the source for ALU. The first input, read data 1 comes from here, read data 2 comes from here, and it goes via the 0 of my mux, which is going to be connecting to ALU SRC. So the ALU SRC status would be 0 for R-type instruction because I go via this way. So ALU SRC status is 0. Now comes mem to reg. So mem to reg is the one that is in the last part of the diagram. So what will happen? Do we use this section at all? No, I am not at all using this section because my result is available right here after the ALU has computed the addition. So I take the result from here, I go here, I go here, I go via this way. So 0 is the way via I am going, and that is the status of mem to reg is 0. Now, since my result is available here itself after the ALU has computed the result, I will go via this 0 and I am getting connected. So the status of mem to reg is 0. I am not using the status 1. Let me clear the screen again so that you will have a clear visibility. So mem to reg is 0. Now I get the result out from here and it is to be returned back to a register specified as RD. Hence my write signal, register write should be high. Otherwise I will not be able to write the content into the register that I want to write. So hence it is 1. Now do I read anything from memory? No, I do not read anything from memory. So it is 0. Do I write anything into memory here? No, I do not write anything into memory. So it is 0. Do I do any branching? No branching, hence it is 0. The status of ALU op 1 and ALU op 2 should be 1 and 0 always for R-type instructions. Remember it. That's it. It's made so simple. We are going to the next type of instruction where we are going to again see the values which are set, reset, asserted, deasserted based on the operation. Now it is load word. What is load word all about? Load word will help you in taking this offset with the content here in this register, adding it together, go to that memory location, retrieve the content and put it back onto a register specified. Load will load the register. That's it. It's a very simple operation We have explained this enough in the previous session, so let me not waste time there. Let us simply track the status of the signals. What is REGDST? Do I use RD? No, RD does not come into picture here. I am using only RS and RT. I am using only RS and RT, and it is also highlighted here for your perusal. So you can see RT and RS. It's very simple. So status of REGDST is 0. Now ALU SRC is here. The first input comes via read data 1, so no problem. The second input comes via this offset, which is getting converted to 32-bit, and it goes via this 1, which means the status of ALU SRC should be 1. Simple, right? Correct. Now we compute the total address now. The address will be computed here, and the address has to be, the address is nothing but the location where it is like this. That is a location from where we need to extract the data from. We are not writing any data from there, writing data to there. Instead, we are extracting the data from that location. So mem write will not come into picture because we are not writing anything, but mem read will come into picture. So mem read is 1. Simple. Now we have read the data. The data is available in the memory location that we are talking about. So the data comes from this memory location. I read the data from the memory location. So mem read has to be high, and then I need to write the data into the register that I have already selected. So I need to get this way, just as R-type instruction. I need to get this way, but it goes via 1 this time. Now let us explain it once more because it could be slightly confusing. I have cleared it. The address is computed here in ALU. I have got the address here. Now I have got the address in this data memory. I'll read the data from the address. I will send it via this 1, and then I write it into the memory location. I write it into the register which has been selected already through the instruction. That's it. So the status of mem write, I am not writing anything into memory, so will be 0. But I am reading from memory, so will be 1. I am writing into the register through this read data through 1 of this multiplexer. So mem to reg should be 1. And then it is very simple. I am writing into the register, so it has to be 1 again. The status of all the control signals for this operation is very clearly explained. It's a very simple thing. Only thing that I want you people to do is draw it once again, try it out. Only then you can get a clear understanding and holding of it. Let's take a store instruction now. Maybe we need not waste time here. We'll go to right away to BEQ. BEQ is nothing but branch if equal. What do you mean by branch if equal? I have mentioned the instruction also here very clearly. You can see that here. I have got S2, S3. I compare the content of S2 and S3, and if they are equal, I will take a branch. That's it. It's a very straightforward thing. I will say that I compare two registers, and if they are equal in the content, I will take a branching. Otherwise, I will not. Now, let us see about it very quickly. What is the status of REGDST? I don't worry about it for a simple reason that I will right away stay with these two registers. So it can be don't care. Now what is the status of ALU SRC? I am not going to take anything sign extended. It's going to be very straightforward and it is read through this. So ALU SRC is 0, which means ALU SRC is 0. Mem to reg, I don't care because it is all branching and it goes away from this control. So don't care. Whatever be it, I do not have a problem there. Now register write. Are we writing anything into register in this entire operation? No, it is just branching. So register write is 0. Mem read. What is mem read? Are we reading something from memory? No, we are not reading anything from memory. Mem write. We are reading anything? No, we are not. We are writing anything? No. So this also goes 0. Now, do we take a branch? Yes, certainly it takes a branch and it has to be 1. The status for ALU op 1 and ALU op 2 for branching is always 0 and 1. Please remember it. That's all. It's a very simple thing. The only thing that you need to remember is with respect to RS and RT, ALU SRC. That's all. It's a very simple thing. It's a very easy and understandable concept for you guys to take it further. Now in the exam paper, they will not stop with this. They will ask you to trace the path for any particular instruction. For example, they may ask you to trace the path for R-type instruction. Then what will you do? What are all the components that are involved in this R-type operation should be highlighted. Very simple. The instruction is read from instruction memory. Highlight it. RS, RD, RT, all the three are used, highlight it. Register, definitely used in everything, so highlight it. ALU SRC, yes, it is used via this 0 input, highlight it. This ALU used, highlight it. But after that, the data memory is not used, so I have ignored it. So whichever component is used, just trace it, highlight it with a shader or something like that, and that will tell you that you have identified the path for R type or J type or I type instruction, and it's going to be very simple. In my next session, I'm going to talk about very clearly about the jump implementation in MIPS. It's going to be very simple, but at the same time, you need to understand it. Before that, we will quickly go through the BEQ tracing. I need register, I need instruction, I need register, I need two registers for comparison. I will use this input and this input, ALU is used. Now you can see that I have used the program counter, the entire part for program counter is using SLL, which means I have explained you how will the branching happen in my previous session. It happens through a branching when once the data is equal. So the result is 0. I take the result here, I feed it into the AND gate, hence it is branching properly and it takes this path. It is not taking normal traditional plus 4. Instead, it takes the branching appropriately. So this is the only thing that you need to remember when it comes to BEQ. That's all for now. I'll come back to you with more inputs where branching, jumping, to be very precise, it's a tough zone to play. We'll really spend a lot of time there to understand how exactly we can make it easier. Thank you very much for following my channel. I'll come back to you with more inputs. And if you have any queries, you can ping me through the comment section. I'll be able to clarify it, I believe.